Hi, I'm David Eppstein, and this is Acutely Triangulated, Stacked, and Very Ununfoldable Polyhedra. A net or unfolding of a polyhedron is obtained by cutting the surface along some of the edges of the polyhedron and unfolding the resulting cut surface into a polygon that lies flat in the plane without overlapping itself. This process can be reversed to make the polyhedron from a flat sheet of paper by cutting out the net from the paper, folding it up, and gluing the edges together into the shape of the polyhedron. Nets were first published and used by German artist Albrecht Dürer, who published a geometry book in 1525 that included nets for many of the regular and semi-regular polyhedra. The one shown here is Dürer's net for the dodecahedron. The question of whether all convex polyhedra can be unfolded into a net was formulated as a mathematical conjecture by G.C. Shepherd in 1975 and has come to be known as Dürer's conjecture. Despite considerable effort from many mathematicians, we still do not know whether or not it is true. If we generalize the concept of unfoldings to allow cuts in the middle of faces, then every convex polyhedron has a generalized unfolding. Two constructions for this are the star unfolding, which cuts the polyhedron surface along shortest paths from its vertices to a specified point, and the source unfolding, which cuts the surface at points that have multiple equally short paths to the same point. But in this work, we consider only edge unfoldings, in which the cuts are restricted to lie on edges of the polyhedron. Although the standard formulation of Dürer's conjecture considers only convex polyhedra, it's also interesting to study the same question for other types of polyhedra, and what we learn about other polyhedra may shed light on the convex case. We now know that several special kinds of convex polyhedra can always be unfolded. These include the pyramids and the prisms, and several related classes of polyhedra. Every convex polyhedron can be stretched to form a polyhedron that has an unfolding, and in hyperbolic space, every ideal polyhedron, a polyhedron whose vertices are all at infinity, can be unfolded even into a convex polygon in the hyperbolic plane. In the other direction, certain non-convex polyhedra do not always have an unfolding. These include polyhedra with axis-parallel sides, even with all of those sides restricted to being topological disks. And they include polyhedra that have the same combinatorial structure as convex polyhedra, even when all of the faces are triangles and there's an interior point from which the whole surface of the polyhedron is visible. The results I'll be presenting today are motivated by a recent paper of Joe O'Rourke on unfolding nearly flat triangulated disks. One consequence of O'Rourke's work is that if a convex polyhedron has acute triangles for its faces, with angles bounded away from 90 degrees, then its surface can be cut into a bounded number of pieces that can all be unfolded. This raises two questions for us. Do acute triangles or triangles with angles bounded below 90 degrees make unfolding easier in the non-convex case? And more generally, if a polyhedron cannot be unfolded into a single polygon, how many pieces do we need to cut it into? The main new result in our own work is that there exist polyhedra that, from a high level, look well behaved. They have the same combinatorial structure as convex polyhedra, all of their faces are acute triangles, and all of their angles are bounded below 90 degrees. But when you get up close to them, they turn out to be monstrous and kind of pointy. Not only is it impossible to unfold them into a single polygon, but the number of pieces you need to cut them into in order to unfold each piece into a polygon can be linear in the complexity of the polyhedron, for polyhedra with arbitrarily large complexity. We build our ununfoldable polyhedra out of smaller pieces that we call hats. These are triangulated disks formed from 9 triangles. The outer 6 triangles of the hat, its brim, alternate between two kinds of isosceles triangle with the same side length, one with an apex that is nearly a right angle, and another whose apex is very sharp, close to 0. The bases of the sharp triangles form a small equilateral triangle near the middle of the hat, onto which we attach 3 more sharp isosceles triangles, forming the peak of the hat. At the 3 vertices where the peak of the hat connects to the brim, the angles of triangles incident to the vertex add up to more than 2 pi. This means that in order to cut it into one or more ununfoldable pieces, we need to cut at least 2 edges at these vertices. The only way to do that while leaving the hat in one piece would be to cut a single path from the boundary of the hat to the vertex at its peak. But this cutting does not work, because when the 6 brim triangles are unfolded, they don't leave enough room to attach the 3 peak triangles without overlapping. Therefore, in any unfolding into a single piece of a whole polyhedron that uses a hat, we have to include a cut path that goes all the way across the hat. A similar type of hat was already used in our previous work on unfolding at CCCG 1999 and in CGTA 2003. The analysis from the 2003 paper required negative curvature at the middle vertices even after removing a spike triangle, which forced the outer triangles of its hats to be obtuse. In contrast, our new analysis of hats works even for some hats in which all triangles are acute. We can form an acutely triangulated ununfoldable polyhedron by replacing all 4 faces of a tetrahedron by hats. As we already saw, to be unfolded, we need a cut path that passes all the way across each hat from one vertex of the tetrahedron to another. There are 4 hats, and so we have 4 cut paths connecting the 4 vertices of the tetrahedron. But a system of 4 vertices and 4 paths cannot form a tree. It must form a graph with at least one cycle. By the Jordan curve theorem, this cut cycle separates the surface of the polyhedron into 2 pieces, preventing it from having a single piece unfolding. To construct a polyhedron that requires many pieces in its unfoldings, we start with a polyhedron that has many equilateral triangle faces, and then replace all of those faces by hats. A polyhedron with many equilateral triangle faces can be formed by subdividing the faces of a regular tetrahedron, octahedron, or icosahedron. If we start with a polyhedron whose edge length is 1, and subdivide it into triangles of side length 1 over k, we get k² small triangles for each face of the original polyhedron. In the example shown, we started with a tetrahedron and chose k equals 2, so we get 4 small equilateral triangles for each face of the tetrahedron, for a total of 16 equilateral faces. We then replaced each of those 16 faces by hats. In order to cut this polyhedron into unfoldable pieces, the set of edges that we cut within each hat must either separate a part of the hat from the rest of the polyhedron, for instance by cutting off its peak, or include a boundary-to-boundary path of cut edges. Therefore, among all the hats, either we get many cut-off pieces, or we get many boundary-to-boundary paths. The graph formed by these paths and the vertices of the original polyhedron must have many cycles, cutting the polyhedron into many pieces. A more precise argument using Euler's polyhedral formula, V minus E plus F equals 2, shows that the number of pieces is always at least half the number of hats. More or less the same argument, but with a different hat, forms very ununfoldable stacked polyhedra. The stacked polyhedra are the polyhedra that can be formed by gluing together tetrahedra face to face. The figure shows a stacked hat in top view and with its stacking order. As with the other hat, the outer 6 triangles are relatively flat, but the central 3 are very pointy, causing the 3 vertices where they're attached to have total angle more than 2 pi. And as before, unfolding along a single boundary to peak path does not work, so every unfolding of a hat must either cut all the way across it or separate a piece of it from the rest of the unfolding. We don't know whether we produce a very ununfoldable polyhedron that is simultaneously stacked and acute, and we leave that question for future research. In conclusion, we've shown that polyhedra that in many ways resemble nice convex polyhedra can still be very far from having unfoldings. While our work settles some questions on unfolding, it raises more, and the original version of Dürer's conjecture on whether convex polyhedra have one-piece unfoldings remains wide open.